Hello everyone. In this lecture, we're going to solve the mean square error problem for linear regression. So the loss for linear regression problem is the average of all sample losses, where for each sample, it is indeed your prediction, which is W transpose XM minus your target TM. Okay, so this is what you predicted as T hat M. Then you subtract the true value and you take its square. Or equivalently, you can represent it as XW minus T. But the L2 norm square, okay? So here, W is in R to the D plus 1, and X is also in that shape, but Tm, so this is Xm, Tm is in R, and if you make it as a matrix vector notation, then the X, which is known as the design matrix, is the capital M times D plus 1, and the T is R to the M, okay? I put everything together, okay? And of course, J is a scalar. So we also talked about the convexity stuff in general, So the definition of a convex function is for any 2 points, the segment of these 2 points is still in the domain of the function. Okay, so this says the domain of the function has to be convex. And second, this segment should be above this curve, the function curve. Okay, the segment should be above the function curve. This is convex definition. And we mentioned that there's a theorem says let F be a twice differentiable function on some open domain, on some open convex domain, okay? Then the following conditions are equivalent. F is convex. And first order condition, it says for any point X and Y in my domain of F, F of Y is greater than F of X plus the derivative of F at X, okay, of course, with respect to X. Transpose Y minus X, okay? So this says any point, the line tangent at that point, or the hyperplane, the flat hyperplane tangent at that point is the lower bound of the entire function. And the third condition is the second order condition, which says for any point in my domain of F, okay? Okay, so the Hessian matrix of F of X is positive semi-definite. Okay, so with these conditions, we can verify whether a function is convex or not easier than you go with the definition. And the property is, we show that for any local optimum, if F is convex, then any local optimum implies it's a global optimum. Okay. So now we're going to show that this function is indeed a convex function, maybe using the first order condition, maybe use the second order condition, and then, or maybe use the definition. And then we will work with the, we will find one local optimum, and then this is the global optimum, okay? So let's remind ourselves. So our task is to, so, originally my task is to find such H in my hypothesis class J of H, as well as my training data, right? But with the linear regression model defined here, so the hypothesis is a parametric form. You only have linear curves, and it's parameterized by your W or B, okay? B is omitted here. So I can say this problem is equivalent to over my W, okay? J, which is a function of W, okay? But it's also a function of my training data. But you have no control on the training data. What you can do is to optimize this W. Okay. So now, just be a little bit more careful. The X and Y here is different from there, okay? So for the linear regression model, we use X to represent the data features. But when we talk about convexity, they are just generic factors in my domain of F, okay? So what we are going to show is, we're going to show J is convex in W, which is a vector, okay? We're not going to show J is convex in X. This X, the X in the left is different from the X in the right, okay? Good. So how can I show a function is convex? So obviously it's easier to work with the first order condition or the second order condition because the function here is differentiable. You see every component is smooth. For example, the difference, the square, the summation, the average, everything is smooth. So this function is very nicely differentiable. Then it's a good idea to work with the first order condition or second order condition, the derivative based conditions, okay? So now I'm going to take the derivative. So the derivative of J with respect to W, okay, it's not with respect to X. So eventually it will be some function, some vector in D plus one dimensional space. Because when you take the partial derivative of a scalar with respect to a vector, you are taking the partial derivative element-wise and you organize it in the same shape. Okay. So now I can represent the norm. The norm is the L2 norm. L2 norm is induced by the inner product. You can think of it as, so the L2 norm of a vector square is actually V transpose V, right? It's just the definition. So, this definition is square root of something square, then this is V1 square plus V2 square, so on and so forth up to VD square. And then this stuff is, V1 here times V1 here, then it's V1 square, V2 here, V2 here, so on and so forth. They are obviously the same. So now I can say this is XW minus T transpose XW minus T, okay? So don't forget to take the gradient, the derivative, the partial derivative. If I take the transpose of two matrix addition, then I take the transpose of every matrix. So that is indeed WX transpose minus T transpose. Okay, we think of vector as matrix. Then if you take the transpose of a product of matrices, you are taking the transpose of every matrix, but you go with the reverse order, okay? So this stuff gives you W transpose X transpose, okay? So I don't think I have to write it again, but okay. So this stuff is just this, okay? Then I can expand this product, okay? So it's W transpose XW minus. Okay, so you expand like this. You can say T transpose XW minus W transpose X transpose T plus T transpose T. And you observe these two terms are the same because it gives you a scalar. Then if you take the transpose of a scalar, you get the same thing. So if I take the transpose, it gives me W transpose X transpose T. Okay, it's exactly the same thing here. So this gives me okay. Now I'm going to take the partial derivative of each term. And by matrix calculus, we know if you have a projected term, then the the partial derivative of the vector is 2SW. Okay. So this is similar to the scalar case, for example, x squared, right? X squared, and you take the derivative, it gives you 2 of x. Okay, or maybe you can say k times x squared. Then if you take the derivative, it gives 2kx. Okay, similar. But this is the wrong way of proof. This is some good intuition, but if it comes to proof, you have to prove it in a rigorous way. But still good to memorize things. So now, if you take the derivative of W, you get X transpose T, right? So suppose this is my some vector X, and this is my Y, okay? So this is X transpose. And when you take the derivative of the first element, you get that. When you take the derivative of second element, you get that, right? So it's almost X. But after you take the partial derivative, you would organize all the things, all the partial derivatives in the original order. So you still have a column vector, so it gives you the transpose. So it should be T transpose X, okay, transpose, which is X transpose T. But now I forgot 2 here. And T transpose T is a constant when you take the partial derivative with W. Okay. And if you take the second order derivative with respect to W, then you get 2m times 2s. So this term becomes a constant in terms of W. Okay. And you get 1 over m times s. And I know s is defined as x transpose x. Okay. This term is positive semi-definite because for any x, okay, for any maybe vector v, okay, v transpose s gives me a scalar is v transpose x v, which is xv, okay, transpose xv, which is the norm of xv, which has to be positive, non-negative. So this term is positive semi-definite. Okay. So this shows S is positive semi-definite. By definition, it means for any V, for any vector, I take this quadratic form, and it has to give me a positive scalar. Okay. So since the second order partial derivative is positive semi-definite, then it's convex. J is convex in W. Okay. So here the proof uses the matrix calculus. So these things are very standard. I mean, they're very standard matrix calculus, and they are not confusing at all. But maybe in the future, not necessarily in this course, but you may come with very complicated matrix calculus. And the best way to do that is you first check the dimension. Second, check any textbook. You just follow the identities and you get things right, okay? But the complicated matrix calculus will not occur in our course, okay? So these are basic. But what if I don't have matrix calculus? I don't want to do matrix calculus. So is it still possible to do element-wise derivative and I show it is correct? So it's highly possible, right? It's definition. So the proof of matrix calculus is usually also by its element-wise result. So you show compute the element, I get something. And then if you organize all the elements in some matrix or in some vectors, you get a more concise notation. So I'm just going to prove it once again by element-wise derivations, okay? So first, let's go back to this term. So I think I can copy this term. Okay, so this is my J. And I would like to take the partial derivative, okay? So my goal is to take the partial derivative of J with respect to W. So this is a vector, and this is J. So when you consider the partial derivative, or sometimes we denote it by partial J with respect to partial W, where the W is the vector, okay? They're the same thing. So it's actually an organization of element-wise partial derivatives. So forth. Okay, you start from 0 and you go to D. So how about let's consider one element at a time. So let's say for the partial derivative of J with respect to Wi for I from 0 up to D, okay? So that is, I would like to compute the partial derivative of the things. Then I just do the chain rule. So I just apply chain rule. And by doing chain rule, it can be done online, which means you don't have to write multiple equations. You just work with one equation and you continuously append more and more terms or more and more factors or more and more derivatives because it's a multiplication, right? So first I just copy this stuff, okay? So it's a constant. Then the derivative is a linear process. It goes into my summation. So I just put my derivative into my summation, okay? Then you know this is a scalar, so I can call it maybe z. And when you take the z squared, you know, you take the partial derivative, you first take 2 times z, and then you say z prime, right? So this is the chain rule. So I can say 2 times w transpose xm minus tm times the partial derivative of each term, okay? So I would now take the partial derivative with respect to wi for each of the term in z, okay? So where's the term in z? So z is actually w0, x0 plus w1, x1 plus so on and so forth until wd, xd minus t, okay? So I omit m. That doesn't count as bonus point. So what happens if I compute the partial derivative with respect to wi? Of course, you get xi, right? So the partial derivative of c with respect to wi is xi. So I have xi here. Okay, so I have m. Now you observe that there's a summation here. So we can remind ourselves that if you take the matrix vector multiplication, there's an implicit summation, right? So I have an implicit summation, for example. I have a first matrix here and second matrix there, okay? If you are doing matrix multiplication, you are taking one column here, so one row here, with a column here, and to get an element. And you reorganize different rows and different columns as a new row and columns grid, right? That gives you a new matrix. And the summation is for every element here, you compute the product with every element there, and then you take a summation, okay? So this is the definition of matrix multiplication. And here, my summation is over m, so it's wise to put m in this axis and to also put m in that axis, right? It's a very natural stuff. So with this in mind, why not let's put my design matrix as this and as my, okay, predicted value minus t, okay, as a vector, which is also a matrix, but a single column matrix. So you know this vector is in R to the M. Okay, I have M samples, so I have M predictions, and I have M differences. This matrix X is the design matrix is M rows by D+1 features. But I hope that I hope the number of samples becomes the columns. So you have M columns. So I would like to take the transpose of M. Now it goes to D+1 times M. Okay. Then you almost get it. But the dimension is not a proof dimension, it's a necessary condition. To prove that, you need to show you are getting the same thing for every element. So why not, let's try it. So I'm considering a particular I here. Okay, I'm considering a particular I here. So this is my I. Then every element here, so it's the transpose of my design matrix, and I'm taking a row, then it gives me a feature, okay? A feature associated with Wi. The feature is associated with Wi, but with different samples. So that should be Xi for the first sample, Xi for the second sample, so on and so forth until Xi for the mth data sample. And what is that? So this is one dimension in my difference factor, okay? So each of the dimension is how much you predict minus your target for first data sample until how much you predict for the mth data sample minus the mth target, okay? So this is each dimension in my difference factor. So this is this. Then when you compute the matrix multiplication, you are using every element here. Multiply it with this. You have this. Multiply it with this. And you have that. Multiply it with that. Right? And then you take the summation. So now you take the summation and you have this. Okay. This term is something in here. Okay. And this term is just the xi. So that is correct. So this also shows that. So the 2 cancels here. So I don't have to repeat 2. And I don't have the summation, which is I just write things here. X transpose XW minus T. Okay. So, oh, sorry. So this is not equal, but if I arrange all the Wi as a vector, then I get this. Okay, this is a vector. And here, this is a vector. This is a vector, and X are the matrices. Okay. So here, I just showed the element-wise proof of the matrix calculus. And of course, matrix calculus identities are more general than here, but with this special example, we know that matrix calculus is not something mysterious, but you should be extra careful about the dimensions, about the transpose, okay? And if the dimension matches, it's just a necessary condition. Okay. Here we prove that linear regression is indeed convex. Now we're going to solve the mean square error problem with the convex property that we have proved. So we know that mean square error is a convex function of your W weights. Okay. I know the weight is a high dimensional vector, but I can just show it in one dimension, or maybe you can show it in maybe 2 dimensions, but no more. Okay, so this is my loss. So it's a convex function like this. Okay. And by convex function, we know that if you have a local optimum, then it gives you global optimum. Okay. And also we know that if exists some point x with the derivative being 0, such that the gradient, okay, I can call it W, is 0, then okay, evaluate it at W0, W star, then W star is guaranteed to be the global optimum. Because the line here is tangent to the shape, to the function, and this point, it has a derivative of 0. So this line, tangent at this point, is actually a horizontal line. Then every other function values must be greater than or equal to this line. So this is the global optimum. Likewise, you can have a plane here. So if I can find a plane whose partial derivative is 0, is a 0 vector, okay, then every other point has to be above this plane, this horizontal plane. Then the point here is actually the optimum, okay? So this is the optimum. So what is our loss? Our loss is here, okay? So my partial derivative of J with respect to the W vector is actually 1 over M X transpose X W minus T. Then I set it to 0, okay? I set it to 0 because it's a differentiable function. Obviously, everything here is differentiable. And if I can find some point whose partial derivative is 0, then I win. If I don't find a point where the partial derivative is 0, I can seek other solutions. So let's first try it. If it's set to 0, then this term cancels out. So I don't need the, am I right? Okay. So the bracket is here. So I don't need this term. So I only need W X transpose X W minus X transpose T is 0, okay? So this holds for any matrix and vectors. So I can move the minus term to the right-hand side of the equation, it works. The only thing tricky here is, if it's a scalar, right? If it's a scalar, like 3 times W is 4, then, obviously W is 4 divided by 3. But here it's a matrix. If the matrix is invertible, then we can say W is X transpose X inverse X transpose T. It's invertible. If X transpose X is not invertible, okay? If it's not invertible, then we can use the pseudo inverse. This is known as the more parallel pseudo inverse. And you can check the reference I posted for the details. But we're just going to explain what does it mean by not invertible. So a matrix is not invertible, it just means it's not full rank. Not full rank. Or maybe some eigenvalues are 0. So it's similar to, 0 times 1 is maybe some number, okay, any number. Then you cannot put 1 over 0, it's invalid. But why could this matrix be non-invertible? So one of the reasons is maybe you have duplicate features. Duplicate features. Suppose you have a feature like the weight of an object, you measure it by kilograms. You have another feature, you measure it by pounds, and they are linearly dependent, then it's not invertible. In this case, you can just apply the more parallel pseudo inverse and it will work for you. But the other case is you have more features than samples. Okay. So in the usual case, our X is a tall matrix. Okay, so we have a lot of data samples, and for each of the data sample, we have a few features. So it's a tall matrix. So I say M times D or D plus 1, I just omit plus 1. Then if you have X transpose X, then it gives you a fat matrix times a tall matrix, right? So this is X transpose, which is D times M, right? And this is X, which is M by D, and eventually it will give you a small square matrix with D by D. If you don't have duplicate features, then in the usual case, it's highly unlikely that it's non-invertible. But maybe we have more features than samples. So in this case, my X would be a fat matrix, okay? I use another color. So my X could be a fat matrix like this. So I have a few samples, but for each of the sample, it's represented by many features, like 1,000,000 features. Okay, it's still M by D, but it's fat. So in this case, if I compute X transpose X, it becomes a tall matrix because it's X transpose. It's a tall matrix times a fat matrix. Okay, it's X. It's still D by M and M by D, but this time it gives you a very big matrix, D by D. Then for this matrix, the rank of the matrix is most D, at most M. Okay, and we know that the M is less than D, then the matrix is not full rank, it's not invertible. So what if you have a non-invertible matrix in this case? Okay, so can I still apply the more parallel pseudo inverse? Mathematically, yes, you can apply the matrix and it will give you the, in both cases, the solution, the optimal solution is not unique. And the pseudo inverse gives you the least Euclidean, the least L2 norm, least norm, Euclidean, least norm solution. Just like, suppose I have one point and one feature, okay, but I extend it by a trivial feature, so it gives you a bias term. So now I have two parameters to estimate, right, B and W. So you can fit infinite many lines across this point. You have a perfect match, but the solution is not unique. So if you have the pseudo inverse, then it gives you the solution that has the least norm. So it just solves the problem if you have the duplicate features. But what if you have more features than sample? It still gives you the least norm, but the prediction could be very arbitrary, right? Suppose you have 1,000,000 features, like you have the gene, okay, you have the gene of an animal. Or maybe you can represent it by genotype. And you want to predict the phenotype. For example, I would say my prediction is how much an animal weighs, okay, the weight. So the weight. So in this case, if you have 1,000,000 features, usually you don't have that many samples. Like you have a few hundreds animals, that's enough, right? Why we can't have 1,000,000 of animals? First, it's very expensive, right? It takes a lot of time and effort to grow an animal, and then we test the gene. It takes a lot of money and time. And second, you have ethical concerns, right? It's not ethical to kill too many animals, even if it's for research. So maybe you have 100 animals. Then even you apply the pseudo inverse, it gives you some results. The prediction is almost arbitrary because I can fit any line and then I can change a little bit. It perfectly match my 100 samples, right? So it shows that your hypothesis class is too powerful. And even if you apply the pseudo inverse, it solves the numerical issue, but it doesn't give you meaningful solution. But still, this is a valid machine learning task and it's doable. So the solution to that is by sparsity. Okay, so we add some sparse constraints. For example, I allow you to pick at most a few features, like 10 features, roughly 10 features, maybe 8, maybe 12, or maybe 15. So you can pick at most a few features, and you can decide which features you pick. And after you pick the features, you learn the weights for those features, or you can jointly learn the weights or pick the features. And as long as your model is sparse, I only have a few features. But if I have maybe several hundred samples, then the learning is still feasible. So this case is doable, but you have to add some sparse constraints, and we will touch this in future lectures. But the pseudo-inverse will not give you meaningful result in this case. So if you find your matrix X transpose X is not invertible, if it's not the reason that you miscollected features, you have duplicate features, then it's still not good to apply the pseudo-inverse. Okay. So just to summarize a little bit. So in this video, we'll talk about mean square error. It's a convex function, just means it's curving up. And we know for convex functions, if you have the local optimum, then it gives you the global optimum. Or maybe you have some point whose derivative is 0, then it also gives you the global optimum. Then we just compute the partial derivative of J with respect to W, and we immediately get W is X transpose X inverse XT. Suppose it's invertible, okay? So X transpose T, am I right? Yes. You can represent the optimal solution by a formula or by an equation. So this is known as the closed form solution. Okay. So the advantage for the closed form solution is, first, it's simple. If you write the Python code, you can just do it in one line, right? This is well supported by any numerical packages. And second, if my numerical computation is precise, suppose we can represent real values in my computer, then if you compute the inverse, if it's invertible, then it definitely gives you the exact result. So if the computation is precise, numerical computation like the inverse is precise, then the optimum is precise. Okay, so this is different from, for example, gradient-based approach. You are walking around and you see where it's best, so you may not be settled to the precise optimum. Maybe you are around. Okay. But what is the drawbacks of the closed form solution? First, it may be numerically unstable, actually. Okay. So previously I say, if it's numerically stable or numerical precise, then the optimum is precise. But in reality, it may not be precise. For example, you have duplicate features like kilograms and pound, and then maybe you have some noise, so they are not exactly the same, and it's still invertible. But in this case, you can have a huge noise due to the numerical computation in our computers. We have to compute things by quantized numbers. Then you can it gives you unstable results. Then maybe you believe this point is your optimum, right? But it's still very far from your true optimum. And also the complexity for inverting a matrix, I don't know how large, but I guess it's roughly cubic, or maybe with better algorithm, maybe you can get square, but it's more than square, okay? I don't know what is the number, but it may be slow if your dimension is high, okay? So, inverting a matrix is not very fun. So the other drawback, not necessarily for MSE, but the drawback for closed form solution in general. It's usually rare. Many problems don't have closed form solutions, right? So suppose it's not a linear regression, or suppose it's not a linear function, then probably you don't have the closed form solution. So it's very rare in real machine learning models that you can find a closed form solution. But sometimes you can find a subproblem, which is closed form. So usually, if the closed form solution is numerically stable, and if it's computationally efficient, you should always try a closed form solution first. Because after you have the numerical optimization, you eventually get your closed form solution. So you should always try the closed form solution first if it's efficient or it's numerically stable, and if you can find a closed form solution. Otherwise, you seek other optimization. Okay. So this is pretty much for this lecture. And this is a short lecture, but it doesn't mind, it's a self-contained topic. In the next lecture, we're going to talk about how to solve the problem by numerical optimization. See you next time.